So we've seen how the non-parametric world extends to our t-tests, and we've had two flavors of t-tests. I've really focused on the paired t-test and the two-sample t-test. Of course, we can, if we know how to do a paired t-test, that also extends over into a single sample t-test. But the examples of single sample t-tests, I don't really think that there are that many practical examples that we might want to look at, so I'm not going to focus on that too much. Of course, the next thing that we covered in our parametric world was the ANOVA test, so it's natural to think that we would have an analogy for that in the non-parametric test world. So here's the setup. We've got some rare and endangered sea snails. So again, you can see the phrase rare and endangered means that it's going to be quite difficult to get some samples for these guys. So we might not be 100% confident in the movement or the distribution because it's rare and uncertain. We have quite limited information here. So we might want to look at the way a non-parametric test would work. We don't feel comfortable appealing to the assumptions of the ANOVA model. So what have I got? We're going to look at their movement at different temperature levels. And the test that we're going to perform is called a Kruskal-Wallis test. So this test is directly analogous to the ANOVA test. And from the test that we've already done, you can imagine the way that this is going to work. If the ANOVA test worked on the means, this is going to work on the ranks. So let's look at our data here. So I've got three groups. I've got three different temperatures, okay? So I've got observations on three groups. So I don't want to jump straight into just t-tests, or in this case, my equivalent of Mann-Whitney tests. I want to compare the three groups as a whole. So what would I do? Well, if I was in the parametric world, I would use the ANOVA test. So let's just recall the ANOVA test. We said, well, with the ANOVA test, we look at the variation between the groups and we look at the variation within the groups. We look at the ratio of those two values, and we say that this ratio follows an F distribution. All right. Practical decision rule from us: large p-values lead to us not rejecting the null. Small p-values lead to us rejecting the null. And the null is that all the group means are the same. So this was our statistic. We have here our F value. What do we have? We have the standardized between group variation divided by the standardized within group variation. If this ratio is large, we reject the null that all the groups are the same. So if there's lots of between group variation, that's a sign that there are true differences in the groups. Similar story when we look at the alternate sort of case scenario that we might have, which is if we have very little between group variation and lots of within group variation, you can see that the way the ratio works is that we would get a small number, and with a small number, that would be a small f number that would be associated with a large p-value, relatively large, getting above 0.05 anyway, and that would be a sign that there are not true differences. So how does our Kruskal-Wallis test work? Our Kruskal-Wallis test works in exactly the same way as our ANOVA does, except we replace the actual values with their rank observations, okay? So we're looking at the difference between the group mean ranks and the grand mean rank, all right? So we replace the individual values, the numerical values, with their rank order. Very, very similar to the way that we've worked with our Mann-Whitney and with our Wilcoxon test. This follows a distribution that looks very similar to F. It's a chi-squared distribution. Practical decision rule is that low p-values lead to rejection of the null of no differences in the mean ranks. Okay, so we're looking at the standardized between group variation using the ranks divided by the within group variation using the ranks. So same concept, large number. If there's lots of between group variation using the rank order, and they're not much within group variation, this is a sign of true differences. The way that we will detect that is via a small p-value. The converse scenario is of course also true. If we look at the standardized between group variation relying on the rank data, and that's quite small, the within group variation is large, we get a small number divided by a large number, small number. So small chi-squared values are observed with p-values that are greater than 0.05, and they lead to us failing to reject the null of no differences across the groups. So it's not differences in the mean, we still use that saying for no differences across the groups. So what do we need to do? We need to take our raw data and we need to convert it into rank orders, which is what I've done here. And you can see here that the amount of movement at temperature 18, generally these are the high levels of activity. As we go to a temperature of 20, we've got lower levels of activity and even further levels of decline when we're at 22, I think. So if I just plot this data, so the plot that we're actually going to use will be exactly the same as if we were doing an ANOVA. So we know that the plot that would match this for an ANOVA is a box plot. So we would have a box plot and we would plot the data on the original scale. Okay, and this is what it would look like. So you can see it doesn't look like there's actually much of a difference going on between 18 and 20, but it looks like there maybe probably is a difference with that 22 group. Now, if we plot the rank order of the data, it's going to move around a bit. So remember these guys up here, these are going to be ranked 1, okay? So these were the most movement. So we've ranked them from highest to lowest. So when we're ranking them, the lowest ranks are going to be high numbers, okay? So these are going to come into ranks 1, 2, 3, 4, 5. These are going to be ranks 25, 30, and so on. Okay, so the shape is going to look a bit different when we look at the ranks. So we don't actually plot the ranks, but just so you can see what's going on, this is what we have. So I've plotted here the mean rank. So that's the mean rank of the data. This is the mean rank for each group of the data. And here are the actual observations for in terms of ranks for the 3 data sets. So you can see quite a lot of overlap between these guys, some modest overlap between these two, and very much clearly these guys and these guys are quite different. So that's what it looks like on the rank order. Remember, the plot that you're going to want to create is going to be the box plot, just as you would for an ANOVA. So it's really quite easy for you. So what's our test structure? All the groups are the same. So not all the group means are the same, just all the groups are the same. So this is a very, very general setup for the null. The alternate, at least one is different. Not all of them are the same. Alpha, always use 0.05. And you can see that the way that we implement the test is very much like we've seen for all of our other tests, with my data, the test name, so it's Kruskal.test, the y variable, the measurements, and then the factor variable, the grouping variable. And then when we want to go on to pairwise comparisons, we still have the same problem that we've seen with other multiple comparisons, which is the increase in the type 1 error rate. So we have a specific function for doing this for us, which is the pairwise Wilcox test. So it's going to apply the Holm adjustment for us by default. So we have the same problem with these tests of multiple comparisons, increasing the chance of a type 1 error. We have the same solution pre-programmed for us, which makes our life very easy. So what does this sort of test look like when we implement it in practice? So here is with my snails data set, the Kruskal test, my response variable is, or my y variable was minutes, temperature was my factor variable, it's conducted the Kruskal-Wallis rank sum test, I've got a chi-squared value, I look at the p-value, the p-value is relatively small, well, it's clearly much less than 0.05, therefore we reject the null. And based on our visual inspection of the data, we shouldn't be too surprised that we're rejecting the null. Okay, we go on to the pairwise comparisons, follows the same format that we've seen before with the snail dataset, apply the pairwise.wilcox.test function. So that's, automating my idea, and you can see it does tell me that I've got this Holm adjustment going on, and we read these off again. So 18 not different to 20, 18 different to 20, 20 different to 22. All right, and you can see that we get these warnings. The warnings are generated just because we have a tie. Okay, so now I've explained exact p-value. What does that mean? It means at the 3rd or 4th decimal place, we're starting to get some inaccuracies. We are not worried by the 3rd or 4th decimal place. We've made our decision rule at the 2nd decimal place. So we can be quite comfortable in ignoring those warnings. and that is an opportune time for a break.